All right, so we were talking about uncertainties, okay, and so utilities. This was somewhere our last slide, okay. I won't cover the rest of it. I mean, you can go and look at the video of the Berkeley. What we were looking for here was, so I don't necessarily call it important from our exams perspective, but I mean they cover a lot of off-topic things in this, so no explanations, nothing. Now in this case we saw, क्या था इस केस में? So in this case we saw continuity means if I prefer A over B and if I prefer B over C, right, then by transitivity A preferred B over preferred C is fine. But what this is taking care of, I think, is, see, probability of A is, so probability of A is P, probability of C is 1 minus P. Then this says there exists a P. So if this so happens, right, if A is greater than B is greater than C, I mean if I prefer A over B over C, when will I prefer A over B? Just talk about A over B. See, all this says there exists a P in between. So all this says is there exists a P in between, right? So there is a continuous thing. So let's say so how do I put it? I had thought of an argument last night. Okay, let me do it. You first go through Berkeley lectures, okay, and then if any issues you can come and talk to me. But so I'll just skip through these slides. So what we care about is, we just care about this numbers called utility. If utility of A is greater than or utility of B, then basically I say that I prefer A over B. So this utility is a number assigned. If that number is higher, I prefer that thing over B. Okay. And then they talk about all these kind of things, human utilities. I won't really go into this. So, you know, things like so these are good examples if you want to go through that, right? In one slide they talk about a lot of things like insurance and so on. So I don't really want to go inside any of this. I don't feel. So all these things, right? Go through that, it will make sense there. Not in my class. What do you think? No. Okay, but they are, I mean, good, nice to hear those 15-20 minutes if you go and look at that, right? So for example, this one, it's a nice example how things work for humans and so on, but won't really go into this, right? So for us, what are utilities? Just एक line में we want to be able to assign numbers so that we can talk about preferences. That's it. Okay. So let's go to MDPs now. All right, let's start with this. Right. All right, so we start with MDPs now. MDPs are basically nothing but this marks the formal start of reinforcement learning for us. So Markov decision process. Whenever you see Markov, what does it mean? I mean, at least in computer science or in maths. In which case do you use Markov? Heard of it before? Have you heard of this name Markov before? How many of you go for yes? No? In which, where did you hear this? Statistics, probability, in सब में नहीं किया? You must have done that. Okay? So Markov decision process. Until now we were assuming things were deterministic. Okay? At least our actions were. So now think of it this way. A maze-like problem. An agent lives in a grid, for example this one. Walls block the agent's path. So these are walls. Okay? For example, the agent can't go there or here. Noisy movement, this is important, this was not there until now. Noisy movement, actions do not always go as planned. 80% of the time action north takes the agent north if there is no wall. 10% of the time north takes agent to west. So let's draw it. If you are here, you take north, 80% of the times you will go north, but 10% of the times north takes you to west. And 10% of the time east. If there is a wall in the direction, the agent would have been, if there is a wall in the direction, the agent would have been taken, the agent stays put. Okay? Think over it. Okay? So just this. If you want to move up, you will go up with probability 0.8, but with probability 0.1 you will go right, with probability 0.1 you will go left. Okay? So for example, if you are here and if you take a action north, the probability that you will reach here is only 0.8, 0.1, 0.1 here. Okay? The agent receives rewards each time step. This is important. A small living reward at each step can be negative. Big rewards come at the end. So if you see here, there is a big reward plus 1 and a small living reward at each step. It can be good or bad, so you have plus 1 here, minus 1 here. Goal is to maximize the sum of rewards, and this is what we have been doing until now throughout the course. So we just talked about this. You are here, you take action north, you go north. This was deterministic. With probability 1, if you take action north, then you will end up in north. In this case, if you are here, you take action north, you might end up here, you might end up here, and you might end up where you didn't want to go. Okay?
Sir, but agent to मेरे control में ना, so why not I do north with what probability? Why would that be?
Anybody to help me out here?
सर लाइक वो तो जो गेम है उसके ऊपर है कि अगर यूजर अगर उसको नॉर्थ से कर रहा है तो वो गेम पे डिपेंड कर रहा है कि नॉर्थ जाने की प्रोबेबिलिटी उसकी 0.5
Okay.
वो लेफ्ट या राइट ही जा सकता है उसकी प्रोबेबिलिटी 0.5 लेकिन अपना एक्शन नॉर्थ की तरफ है.
Okay, anyone else? See, in real world, let's say this is a robot, right? You want it to go forward, but for some reasons it slips, goes this side.
Model issue there.
Yes. Okay. So this is taking care of things which are beyond your control, which are beyond your design. You design things in a manner, but things don't work as we design them, right? So this is what it is. It is taking care of the other things that you didn't take care of. So if you want to take care of those other things that can happen, this is probably not the right model. Maybe go for this one. Okay. क्या चीज? I don't know what is training right now. We are just trying to bring a model. That's it. Okay. So Markov decision process. What is a Markov decision process? Those similar things that we have seen before. A set of states, a set of actions, a transition function. This we need to look at carefully. So transition function is a probability that A from S leads to action from state S leads us to S prime. Okay, that is probability that you will reach to S prime given in state S you take action A. Also called the model or the dynamics. ये सारे नाम्स इंपॉर्टेंट है अपने लिए. A reward function. What is a reward function? What is a reward function? Exactly analogous to transition function. What is that? If you are in state S, you take action A, you reach to S dash, S prime. So whatever reward is given to you, we have already talked about a small reward, big reward. Okay? Sometimes just RS or RS prime, a start state and maybe a terminal state. So most of these things are same as before. This thing has changed, this thing has, in fact, right? So MDPs are non-deterministic search problems. They are search problems, we have seen them before, but they are non-deterministic search problem. On way to solve them is with expect-max search. So one way to solve them is expect-max search, and we'll have a new tool soon. Then, so how do we solve it?
Here's a grid world. For now, ignore the numbers. They'll become important later. And you can
So
also
to
watch-
start with, we have all so these are the states available to us. This is where agent is not allowed to go. Okay, so you can't really go into that state. All numbers here 0.
Here at the bottom, which is going to echo what I press. So what I'm going to try to do is I'm going to try to get the agent, which here is the blue dot, I'm going to try to get it into the good
So you start from here.
square, which is up here. Remember, there's a +1 there. And I'm going to walk it step by step. And I'm going to go to the right and up. You won't be able to see what I press except when it echoes below. The important thing is usually the key I press happens. But sometimes the agent slips. So I'm going to press east. And look, you can see I took the action east, but I ended up where I started. I'm going to take it again. I went east. I'm going to try east again. It worked. I'm going to try north. Now this is a little tricky, because if you think about this square here, I'm taking a little bit of a risk, because this lower exit here is actually a pit. Hopefully I won't fall into it. 90% chance. It worked out. I'm going to go east again. And that succeeded. I end up in this square. Now in the exact formulation of grid world here that we have, when you get into one of these exit squares, you're not done yet, you don't receive your reward yet, you have to take a special action. It's the only action you can take. It's called exit, and so now I'll be forced to take the exit action, and I will receive my +1. And if I scroll through the rewards, you'll see I got a bunch of little negative
So it says average return from start state is 0.4. Why 0.4?
Very end, I ended in the exit state. I took the action to exit, and I got a reward of 1. That's how it works in grid world.
So we'll come back to those examples anyway. Markov generally means that given the present state, future and the past are independent.
Here's grid world. For now, ignore the numbers. They'll become important later. You can also watch down here at the bottom, which is going to echo what I press.
Okay, so it runs in full screen as well. Markov generally means that given the present state, future and the past are independent. Okay, and this is true for almost everywhere you go. Markov process is this. Given the present state, future and the past are independent. For Markov decision process, Markov means action outcomes depend only on the current state. So probability, so what is this? What is this whole thing? So probability that my state at time t plus 1 is going to be S prime, given that at time t state was ST, action taken was AT, given that at t minus 1 state was ST minus 1 and action taken was AT minus 1 and all the way until S0 A0. So what is this line stating? That I going to S prime depends on this full history, right? This is given that or such that, so every move is given to you, every state is given to you, which action was taken in every state is given to you. But if it is a Markov decision process, then this whole thing is equivalent to just this. What is this part? Probability that I reach in state, S prime at time t plus 1, it depends only on at timestamp t and action taken at timestamp t. It does not depend on t minus 1 onwards. Okay? This is what Markov means whenever you talk about in computer science. Markov stands for this. Present state, future and past are independent. Given present state, future and the past are independent. So this is just like search, where the successor function could only depend on the current state and not the history. Example? Example? Sudoku? Okay.
0 plus 0 plus 0 plus. टिक टैक टू टिक टैक.
कैसे?
मतलब अगर मैंने x कर दिया, so what my adversary will say won't be depending on the previous moves.
Okay, more examples. Let's say you are trying to run a robot, you are trying to run a helicopter, you are trying to make a helicopter. So where your robot will go from this state, right? Next state depends only on my current state and current controls, right? Similarly for all these reinforcement learning things that we'll see. Now what are policies? All these terminologies, they are important for RL. So in deterministic single agent search problems, we wanted an optimal plan or sequence of actions from start to a goal. So when we were solving, tic-tac-toe up there or chess or whatever, in in single agent, so not tic-tac-toe or chess, but in single agent search problems, we wanted an optimal plan. What is this? You start from a start state, you want to go all the way to goal state. We were looking for a path, right? And that was called the plan. We wanted an optimal plan or sequence of actions from start to a goal. For MDPs, we want an optimal policy. So what was plan there becomes policy here. What is this policy? What is policy? So given a state, it tells you which action should I take in this state. Okay. So policy pi gives an action for each state. ये चीज एकदम ढंग से स्टार मार्क कर लो. Total number of states. So policy pi gives an action for each state. An optimal policy is the one that maximizes the expected utility if followed. So now we are completely onto the phrase that we were saying. So what was the objective of this course? Maximize the expected utility. We are there full on. Okay, no words dropped right now. So an optimal policy is the one that maximizes the expected utility if followed. An explicit policy defines a reflex agent. What does it mean? What was a reflex agent? You are not supposed to think, you are not supposed to do anything, just look at policy, look at the state you are in and take that action. अपना दिमाग नहीं लगाना है. That's what reflex agent was, right? You instantly do whatever. Expecting X didn't compute entire policies. If computed the action for a single state only. So optimal policy when RA is this for all non-terminals S. This says this is the optimal policy. Tell me how come? Maybe this is a good thing. Let's talk about this policy. Where do you start from? Where do you start from? So this particular thing does not mark a start state. All it is telling you, if you are in a state, which action should you take? So tell me, where do you find issues? Look at it carefully. Where do you find issues? So this one, what should I otherwise, I mean, what would I expect? I should take this side, and then from here I should take up, and then here. My goal is to do what? My goal is to maximize the expected utility. Okay. Now, so just pay attention here, and now tell me, what about this guy? Do we see any change? What is R? What does it mean to say RS equal to minus 0.01? So every step that you are taking, that costs you minus 0.01. If I go from here to here, right? If I go from here to here, it does not matter where am I landing. The moment I have taken an action, it has cost me this much. Okay. You have increased R in this case and your policy has changed. So I'll first talk about just these two. Tell me, what is going on here? Right. What is that? See, if you move, so we have seen that if you want to go up, you can go left and right with probability 0.1, 0.1. If you want to go right, this happens with probability 0.1, 0.1 and so on, rotate it everywhere. Okay. So why this state? Why don't you want to go there? Why you don't want to take this action in this state? Yes. If I take this action, then what happens? There is 0.1 probability that I may directly end up in this pit. My game is over. I don't want that. Now, if I take this action, what will happen? So let's say after 10 steps, I will get 1 this side. By if there is probability 0.1, what can I safely say? If I take 10 steps, 10 actions, one of them will take me here, and then why don't we go this way? Because again it takes us closer to this fire pit, we don't want to go there. So we would take this path. Now why does it change here now? Everything else I think, so this guy changes and this guy changes, everything else is the same. Why so? To avoid minus 1, right? But right now I am not necessarily avoiding minus 1. There I was sure I am doing it.
Because here we would likely need 2 plus 1 to match the strike because all arrows are pointing towards you.
See, first of all, what does it mean optimal policies?
Reaching the goal state investment.
Optimal policy, if followed, will maximize your expected utility. Okay. What is our expected utility? What are those numbers for us? Those numbers are R. Okay. These are those numbers, and of course these numbers that you get when you reach to a state. So when I reach from here to here, I don't get anything, I don't lose anything. But what cost do I pay? This much. That's there in my model. Here it is 0.03. Now tell me, on an average, how many steps will I need to take if I need to go from here to here? In that 0.1, 0.1, 0.8 model? 10 steps? Okay? 10 steps for here as well? Now if you were in this direction and if you try for 10 times, how much cost already to take just one step? 0.3, I am removing that minus, okay? So you have already spent a significant amount of cost if you were trying to move this side, okay? Now this will become better if you look at this. Here if you see, this arrow which was in this side, it has now reversed. This guy is this side, this guy was taking you this side, has gone up. This is what we would expect. I mean, this is what I think all of us would have given without any of these informations, right? Now why this? अच्छा बताओ यहाँ पे क्या प्रॉब्लम होगी if I take this one down? So on an average, I may have to go for 10 steps to go that side, and that will already cost me minus 4. That is super expensive. Okay. Last one, and that will help you clear everything. Why this one?
Because that's lower than the average cost.
Because moving one step cost me -2, I better directly go into -1 and end the game. Because if I keep playing, I'll incur -2 at each step. So the best is to directly jump in this fire pit and game over. Questions here? I still want to ask these questions. Why this side and why this side? So these numbers, they impact a lot. Yes.
In the first two cases above,
Hmm.
you were asking about the steps taken to move downwards, but we don't want to move downwards. We want to.
Hmm.
So why are we talking about moving downwards?
So can anybody help me here? Why is arrow down here? Because this certainly avoids this -1. And the cost to move one step is so small that I can afford to take those 10 steps. Right? So even if I try it 10 times, my cost will be -0.1, which is small. I can afford to take this longer path. But here if you see, we are taking this path, because if I take a longer one, -0.4 times those steps plus 1 is going to be actually worse than this one. And for this one, moving one step is greater than the worst cost I could think of. So it's better to jump directly here and not play this game for a longer duration. हाँ,
0.4 वाले में वो arrow उधर क्यों हुए?
किधर? Which one? This one?
Yes, sir.
You tell me.
How did it decide to go?
You tell me why is this guy this side? If you go from here 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay? More questions here. How many of you are okay with this figure? How many of you are not okay with this figure? Not okay?
Sir, वही वाला समझ उसको कैसे पता पड़ा कि उधर shortest path है?
किसको?
वो वाला arrow.
This one?
मतलब वो तो clear हो गया कि
हाँ.
decide कर रहा है, but उसमें उधर भी उधर अगर जा रहा है वो, then it's going एक ऊपर एक नीचे.
नहीं. What is this telling you?
Shortest path तो मिल रहा है, so वो समझ गया.
This is simply telling if I am in this state, take this path. I mean go this side, take this action. The only thing this arrow is telling me, if I am in this state, go right.
तो इसमें वो probability consider नहीं कर रहा कि उधर उधर जाऊंगा तो 0.1 है कि stall हो जाएगा, नीचे जाऊंगा तो 0.1 है कि stall हो जाएगा.
No, it is always considering those probabilities. It is always considering those probabilities, but the cost to move one step is so high that I don't want to do things like I did here. In fact, you don't even want to do this if you just increase from 0.1 to 0.03. I mean 0.01 to 0.03. Right? This was a very special case where your cost to move was so small that you could afford to try this 10 times here. Yes.
But if we are changing arrows along with the cost value, the फर्क क्या पड़ता है? We can design anything.
Right.
We cannot possibly compare, right? Because we are changing arrows along with the cost.
So this means your policies, they depend on these numbers. What are policies? Given any state, tell me which action should I take. Right? So if the penalties are low, I can afford to, entirely. So if I take this action, the probability that I'll go here is 0. But if I take this action, the probability that I'll go here is 0.1. Okay. So I don't do this when my cost to move one step are high. But I can afford to do this when the cost to move one step is small. Okay? More questions here? So I think I'll just stay here.
आज निकालने का एल्गोरिथम होना
क्या चीज?
एल्गोरिथम होना ये रिकॉर्ड फंक्शन का एल्गोरिथम
So I have a question, how do we compute RS?
gradient descent.
No, right now we assume somebody is giving us RS.
Along with the arrows.
No, arrows are policies. This is something that you compute. So if you see here, we want an optimal policy. What is a policy? It gives me what action should I take in every step. Right? So once I have a policy, I don't have to compute anything. I become a reflex agent. Once I have a policy, I become a reflex agent. I look at my policy. Policy says go right, I go right. Policy says go north, I go north.
So arrows are policies in this case and we are
So,
deciding it.
so arrows are basically solutions. Once you reach an optimal policy, that is basically a solution to your problem. So you don't need to look at anywhere anymore because it tells you in every state what should I do. More questions here?
Policy follow, agent policy follow करेगा he is like programmed or it's up to like is it a suggestion for the agent to just follow the policy?
No, it is not a suggestion. It's a compulsion. Right? So, and compulsion to this extent that if you are in a state, you don't have to compute anything, you don't have to think anything. If my policy says go left, go left.
Just like
So if my policy here says go to fire pit, go to fire pit. Right? The problem, however, is how do you compute this, and this we will see in due course of time. So this is our final thing that we are looking for.
Penalty was given and we formed the arrows.
So this reward was given to us, somebody gave us, and then we said optimal policy if R is this, then this. Optimal policy if R is 0.3 minus, then this, and so on. Fine? Chalo. So we are done for today. Right. एक सेकेंड.